So, good morning. I'm going to talk about swarm intelligence algorithms. I do have some demos embedded in a PowerPoint slide, and there's a 50-50 chance of these working. And I think last time I tried to show some, it worked. So chances are today they're not going to happen. If there's time afterwards, I'll be able to show some things moving around. But you'll get the general idea, and maybe that will encourage you to go away and play with these. I'm talking about swarm intelligence algorithms, partly because loads of people are talking about AI at the moment. And when they say AI, they mean Gen AI and things like large language models and ChatGPT. And that's just one small, tiny subset of the whole world of AI. So I just want to give you a little glimmer of there being other things you can do that might be called AI or machine learning that are completely different to ChatGPT. And I personally think way cooler, and an excuse to practice coding things up. In order to do some of the things the large language models are doing, you need to know a little bit about calculus if you're going to roll them out by hand in order to do neural networks. But some other things, like swarm algorithms, the maths is much, much simpler. It only really involves multiplying and adding up, which has complications if you start doing it with floats and doubles, but this is just to get a general idea of how an algorithm works rather than do anything useful and precise. So this is really a little glimmer of AI, but something you might not have come across, or maybe you have, but an encouragement to go away and try writing some code, because it's fun and you learn things. So I'm going to explain what swarm intelligence is, give you an overview of a few different algorithms. There's going to be particles, a brief mention of ants and bees, but the main focus today is going to be cats. That might seem like a strange animal to choose to model swarming. The thing about a lot of AI stuff and kind of blue skies research is people just come out with things that may or may not be realistic, but if they solve problems, that's cool. Like I said, there may or may not be any demos of moving cats. Now, some of you might have heard me speak before. Some of you might not. A long, long time ago, I gave my first talk at the ACU conference in the UK, and I talked about how to code your way out of a paper bag by using some AI and machine learning models. And I cheekily printed off a certificate, and a few people signed it, so this is my proudest possession. If you put some blobs, some shapes, in a paper bag and make them move, you can make them diffuse, but then they cheat sometimes and go out of the sides. But it's it's not clearly defined problem, so maybe that's okay. Yes, the demos, for whatever reason, I don't know, my laptop's now possessed and won't move, but I could just make the green dots go up. So I'd have an X position and a Y position, and just add something in a for loop, up they'd go, and then they'd leave the paper bag. I use the simple fast media library to draw these. I only in the last 10 years or so started trying to draw things in C++. I came into programming writing arcade games in BASIC by copying the code in from little magazines, and then I've played around in Python and JavaScript and learned how to draw there. But each time I looked at drawing libraries in C++, I saw stars and macros and went, a bit. The SFML gives you quite a nice API to use that I've personally found a bit easier than some of the things it's based on, like OpenGL. That's not dissing OpenGL, it's just saying I'm learning still. And if you want to get into drawing things in C++ and you've not tried, SFML is one of many ways of doing it. I found it quite easy. They all do the same sort of thing. You've got a while loop. You process your events, like add something to each of the blobs to make them go up, and then you draw them. So decide what you're going to do, update everything, draw, rinse and repeat. So you get a window to draw things on. You check if someone's closed the window or not. And then we can draw circles or rectangles, or we can say any polygons we want. We can set colours. We can put them in positions. And we can rotate them and move them. My background's maths. So I always think of 0 being at the bottom. But every time I try and draw pictures on a computer, 0's at the top, which kind of makes sense because you usually write from the top and work your way down. So I usually just do a takeaway sum to get things back the right way round in my head. Otherwise I get really confused. So, events, updates and displays. That was just a little intro. If you haven't done any graphic stuff in C++, give it a go. There are lots of libraries out there, and it might not be as hard as you think. The thing I found most confusing was naught being at the top rather than the bottom. So, swarm intelligence. Like I said, it's part of a larger part of machine learning and AI stuff. It's sometimes called meta-heuristics. You're trying to find solutions to problems, and some things you can't figure out mathematically. I think the things I'm going to demonstrate today you can work out mathematically. But there's some things you can't, or sometimes you're not sure what the answer to a problem is. So you could guess, and that's okay. And you could do that pencil and paper, just come out of a guess and go, actually, no, I was trying to make sure I'd got £50 left at the end of the month and I'm going to be £10 million in debt. Perhaps I shouldn't buy a yacht. Right, let's try again. And you just nudge, rinse and repeat, change things, even maybe slightly randomly, and see if you're getting better or not. That's the essence of almost all AI algorithms. Try something randomly, step back and go, any good? Nah. And then change one thing or a few things, a little bit or a lot, and try again. And see if things are improving. What makes swarm intelligence different to some of the other ones is they tend to be called trajectory-based. So instead of maybe just listing possible solutions and changing 1 or 2 numbers, you form an idea in your head of, my solution's going to be equivalent to a point in space, so it might have an x coordinate and a y coordinate, for example, which immediately gives us the paper bags. So each potential solution, and you'll have several, like several bits of paper that you've tried just guessing on, one position somewhere on your 2D screen, but you've got a trajectory as well to form a swarm algorithm. So each of these little blobs is a point in space, and if I was cleverer, I could add a Z coordinate and do 3D stuff, but I can't do 3D graphics yet, so another year. You could do 4D stuff, and then you probably wouldn't want to draw it. So we've got X and Y, I'm going to get 2 numbers out, but they're moving with a velocity, so they tend to go in a specific direction. And that gives you a swarm algorithm. And I'll try and show you why that's useful. Skip ahead to executive summary of what's coming up. That trajectory, if the whole swarm has got an idea of where it is at the moment, how good that place is, how good that XY coordinate is, each individual blob can tend to nudge towards the overall best position. So then they'll all start to move together. Not actually on top of each other and doing exactly the same thing, because we want this randomness, this spread, this idea of exploration going on as well. And that randomness helps with that. It allows you to exploit what you know is the best place so far and explore a bit by randomly just jiggling around. So the de facto example of swarm optimization is called particle swarm optimization. So like I said, you've got an x coordinate and a y coordinate, and you've got this velocity in the same number of dimensions. The x and y solve a problem for you. Might tell you how many yachts to buy and how many sports cars, or something else. And in your while loop, at each point, the next x coordinate is where you were before, plus what you get from the velocity. So in 1 click or 1 second, if your velocity was 10 kilometres an hour, you would have gone 10 kilometres in an hour. And we'd just do this in a loop and it'd just be a number, not dealing with units properly, which is fine. But then you update the velocity as well. So that's how you update the x position. Same with the y, and if you've got z and whatever letter comes after z, conventionally w, of course, any mathematicians in the room, because, yeah, mathematicians aren't very good at spelling. This one isn't. Update x and y, then we update the velocities in each dimension of that. So we take an amount of what we're doing anyway, and that's a number you need to choose up front. And then you choose other constants, 2 other constants. For a particle swarm, each particle remembers its personal best. So we're going to need a scoring function for each x, y position. But it will remember its personal best. And then for all the particles in play, you've got a global best. So you take a bit of what it was doing anyway, like its momentum, but it's tempted towards its favourite place so far. But because it's part of a swarm, it tends to move or flock with what all the other particles are doing. So you get all these things tending in the same direction, but that variety to help them explore. And the little blobs are too small, but they start wherever, and they all start moving together, and then vroom, they've ended up disappeared in the right-hand picture. So you've got that while loop, you've got the randomness initially, and then you've got this random updating of the velocity. And that, if you play around with these, you can get them to swarm around or swoop about and things. Code it up. It's not that hard. And that was just some multiplying and adding up. You can do other things too, like if you've got a grid layout, like a town or something, you can work out a path around by remembering this time an ant, because ants behave like this. It's based on how ants behave. You'll have several of them, they'll move around, but they'll lay a pheromone, which is just a number on the edge of a graph, which makes some edges more tempting than others. And gradually the number for an edge, the pheromone, drops down. And it's less tempting. But if you think about it, what you've got going on is, if you've got a shorter route and the ants go backwards and forwards and lay pheromones each time, that will build up more. Yes, they'll drop down because you'll reduce them each time. But every time an ant goes bing bing on the shorter route, it's laid twice as much pheromone as if it's gone like that. And like that, you can have one ant doing twice as much on the short route as another route that's double the length. And you can use that to work out logistics problems in terms of like routing trucks through grids in cities and other things like that. Another variant is bees. We'll get to the cats real soon now. So for the bees, each bee's got a specific role. So the particles were all moving and having a personal best and a global best thing happening. The bee, abstract bee colony, swarm algorithm, splits this into 3 different roles. You have a scout that goes out exploring, so that's free to move around wherever it wants. So that will just add randomness. That hasn't got the trajectory part. That's just doing the exploring. Goes where it wants. Then you've got some bees that are gathering food. They always go on a trajectory towards either their favourite place so far, or the global favourite place so far. And then you've got someone that's sat at home. So they go and do their thing. Then they come back and they kind of compare notes on what's been best so far. And maybe one of the ones that was staying at home last time randomly decides or is assigned a new role of gathering food from this new better place, one of the scouts has said. So instead of having particles doing that explore and exploit, you separate the roles out and randomly mix them up. I've written about these in a book years ago. You can look loads of these up on Wikipedia, actually, and it's correct and it's good enough to give you something to play with. And all of it has got a while loop, and some adding and some multiplying, and a bit of randomness. So, I promised cats. So let's talk about cats. This was our cat Vim. We miss him very much, so it's dedicated to Vim. There is something called a cat swarm algorithm, and you can download the paper and read through it. It's only about 2 or 3 pages long, and subsequently people have actually been using this for some real stuff, like signal processing and compression and all kinds of things. The trick is how you assign the value to the XY position, or XYZ, or XYZW, etc. position. And then you can encode your problems. But I'm just going to stick with trying to move out of a paper bag. Taking the words from the paper, they talk about creating n cats and randomly sprinkling them in m-dimensional space. We're just having 2 dimensions today. And then haphazardly picking cats. The cats, like the bees, are going to either be seeking, which is like that random explore around a known place, or they're going to trace, like they're zooming to catch a pigeon or something like that. Seen a thing, getting it. That's a lot of words. My executive summary is we've got a while loop, like I said. We start randomly, so cats turn up wherever. We find the best cat out of all the cats, which is hard if these were real cats, but they're not real cats, they're just numbers in a struct, so that's all right. And then they either seek or trace, depending on what mood they're in. And then I've shuffled the cats around, but the way I implemented this was I went, I don't know, the first 2 or 3 are going to be trying to catch the pigeon, and the other ones are going to be moving around. So, position and velocity. And I kept track of whether they were tracing or seeking, just to make the displays different. They're like all swarm algorithms, like I said at the beginning. Position, which is going to be a potential solution, and that trajectory or velocity that drives them towards the better places. And you could start digging into how you'd code that up. I'll zoom over the code, but you can see how you'd do that. The velocity as well wants an X direction and a Y direction. And I kept track of the angles and made little triangles for the ones that are trying to catch the pigeon, so you can see which way they're going. You don't need that for the algo. So, 2 roles, seeking. The people who wrote the original paper saw that like a cat that was mostly being lazy and sleeping, which they do, but kind of fidgeting around a bit. It's moving, but not much. And they come out with all these swanky academic words like seeking memory pool. All this really means is if I've got a cat in that middle position, it might always choose 1 of 5 nearby positions. That's what the seeking memory pool is. And you can constrain how far it considers going. And it randomly chooses one of those. It's more likely to pick the better one. And if I want the cats to get out of the paper bag, I'd assign the top one, the higher score. And I can just use the Y value because I've done maths rather than computer graphics. But I could do it the other way around if I wanted. And this, in the AI machine learning lingo, is called roulette wheel selection. I've got several things. I'm more likely to pick the better one. So if I were to take the y value of everything, the higher y values would be more likely. I might go down, but I'm more likely to go up. And that keeps that ambling around, moving, exploring. The paper itself does this like transformation, so as the worst is never going to be chosen. Whether that's a good thing or not, don't know. I set it up so as I could pass in different functions. So if I'm trying to make the cats go up out of the bag, I can say, right, well, I'm just going to choose the y value, or actually I'll floor it so it doesn't go through the bottom of the bag. I can pass that function in, and then I can vary it and solve other problems, which we won't have much time for. I've then got a value for each potential position. So given the positions, I'm going to call my objective function, and again, that's lingo from AI. This is the function I just passed in that said, just use the y coordinate to give a value to this position. And I want to randomly pick one, but I want a weighted random. So I can use C++'s discrete distribution. But if all the places are equally good, discrete distribution will blow up in your face because you can't give it the same weighting to everything, which really annoys me because I think that uniform distribution is a special case of the discrete distribution. So I had to fight to get all this code on the slide. But basically, I'm finding the weighted fitness of each position and then got this special case for if everything's the same. I just return a discrete distribution where everything's equally likely, otherwise I give you a weighted one. And then I can randomly pick. This is my seeking cat, so it's choosing one of 5 nearby places. I can randomly pick one of those. I did put a static in there, but it made things fit on the slides better. And this got out of hand. I stepped back and looked at the code I'd implemented. I ended up with quite a few statics. You all use C++ random numbers from C++ 11? Yeah, good. I'm never quite sure of the best way of setting things up so as I can swap out to something else if I want to test things. But that's a discussion over a coffee, I think. So we've got our seeking cats. We set up this objective function. What I did was I passed it in so as I could swap out the whole thing and just always choose the best one instead and sidestep the fact I'd left this static Mersenne twister inside my function. Seeking cat's got a move method. What does move do? Well, it updates X and it updates Y. That's all it needs to do. So were this to work, and I'm pretty sure it's not going to, I've got, say, 5 cats, and they'll all just move around. And actually, because I'm adding randomness in a small zone, that's kind of like Brownian motion, if you've come across that before. So they will actually eventually disperse, and they will actually end up ambling out of the bag. Which means I've accidentally solved the problem. If I was trying to find a different point or solve something else, then that wouldn't be much use. The other mode of cats is tracing, so they're after, catch that pigeon. And like the seeking cats, set them up and then they move. But their movement's going to be different. They aren't just going to amble around nearby. So go hunting. And I left the comment for posterity in the source code because cats being cats, or catvim, stood on my keyboard and typed loads of plus signs for me, which was very helpful. But this we are adding to, we're using the velocity here, so I've got current position. I'm going to update the velocity, and this is a bit like the particle swarm, except the cats forget what they're doing, so they don't remember their personal best. I, as the algorithm, just look at the best cat's position overall and pass that in. So I nudge the velocity towards the best position. Then I update that cat with its velocity. So that's going to make it tend towards the best position. So every cat that's tracing is going to tend towards where that pigeon happened to be. Just a bit, just by that R1 and C1. So just those are just, R is a random number and C is some number I chose up front. I just left it at 1, and that means there's some cases that don't solve problems if I distract the cats, which we'll get to. And if I were to be able to run this demo, which I might be able to do from a command prompt afterwards, or we can gather around my laptop over a coffee, they all go and all tend to zoom off in the same direction. That's if I've only got the tracing cats. If I have some seeking and some tracing, I'm doing the proper algorithm, and that's the swarm intelligence algorithm. And the combination of the two means that they will solve more problems. In order to code it up, you need to keep track of various things. So you need some cats, and rather than me using the mixture ratio that it talks about in the original paper, I decided if I set up a vector of cats in advance, I could have, say, 3 of them tracing and the rest of them seeking, or all of them tracing, or all of them seeking, and that was easier to work with than passing in 0.5 and then having to have half of 15 cats doing one thing, which is 7.5 cats. So I went off piece, didn't do it the way the paper said. And that often happens if you're trying to code something up. If you read the business language and do exactly how it's described there, you can end up with some really hard to deal with code. So yes, that's fine. I've got some hard-coded numbers, which with hindsight I possibly shouldn't have had. And I'd be hard-pressed to tell you what the 5 and 2.5 are without going several slides back and looking up what those are supposed to be. So good variable names are useful as well. I think the seeking cats are considering 5 positions, and they're going up to 2.5 times some maximum distance in each dimension. And the trace, that was the weighting, is 1.0, which just means I'm not scaling up how fast it'll go. So, in terms of the implementation, I just, in advance, said, if you get this close to the target you're after, remember I've got an objective function, which gives me a number back. So I can see whether that's good enough or not. If I'm going out of the paper bag, I can see if it's above the height of the paper bag, that's pretty good, and that'll do. If I'm solving other problems, I can say, well, if I'm trying to spend no more than £50 this week, if I get within 50p, that's good enough as well. So you don't always want a precise solution. You can say how close you want to get, and that might be a good enough starting guess to then dig down, do some maths around some of your problem. Or maybe you've solved it and you can buy your yacht and have 50p left, and so on. So updates, that's called in the loop. So in my game loop, it's not a very good game, and the demos aren't moving on the screen, but hey, I'm shuffling the cats, which is, as you can see, sneaky way of switching the cat's modes. So just make the first few always be in tracing mode. So if I shuffle the cats, I'm changing whether they're seeking or tracing. Then we make the tracing cats move, we make the seeking cats move, and then we look and go, there are many cats. This one's solved my problem best this time around the loop. So remembering the best cat each time, and hopefully it's getting better. You can log out the bests value and see whether things are improving or not. Clamp was just to stop the cats going off the screen, but they aren't moving on my laptop today, so That wouldn't have been needed. Like I said, you can drop out your best value, and you'll often see like a bit of a bumpy ride. Now, this is quite a simple problem, because I'm just trying to make the cats increase the Y value until they're out of the bag. Sometimes you will see some chop going on. And if you're playing with some of the AI machine learning algorithms, do like trace out, log what's happening. Write down the parameters you've used. We saw that I decided the seeking cats, there'd be 5 of them, and it would go up to 2.5 times in any of the dimensions. And I left that waiting for the tracing cat to 1. So record your parameters and see whether you see improvements or not. And then there would have been a demo of the cats all moving around and going up. Like I said, if I don't overrun, I might be able to show you one of these afterwards. This is a real simple problem. In real life, you often end up with situations where something looks quite good. If instead of going up, we're trying to go down this time, if things just randomly moved around a little bit, they're quite likely to get stuck in the first dip, in this case. If you're trying to go down, there might be a much lower dip somewhere else. So you might need some bigger random jumps to get over that little nearby hump. And if you've got these so-called local minima or maxima, things that look quite good here, there's a leaf. Whereas over here, whoa, there might be a bigger leaf or something even cooler with, well, cats. So I set the code up so I could put some little distractions in. Because cats get distracted, right? They do. So I randomly set up some special positions. And then because I'd got quite a general purpose objective function earlier, I can have another constructor that takes these special places, and I can use them in the waiting function, which means I can subvert how the function I'm trying to solve behaves. I mean, alternatively, you could set the function up in advance to have these special places, but I was adding deliberate distractions for the cats. What it's doing is, I've used that witch's hat function. Some kind of nods. It's basically this shape here. It means if you buy a specific value, you get loads more out, and the further away you are, it tails off. If I add that to the Y value, you can see in the graph on the right, there's this zone where everything's equally attractive. So for seeking cats in that zone, that plateau, each place is equally likely. And hopefully you can see there how having this other behaviour from the cat going, no, I'm not just ambling around here, I'm going for the pigeon, that will then pull the seeking cats away, provided the seeking cats then get a chance to go into trace mode. So like I said, this is just some adding up and some subtracting to add that special bit to distract the cats. And if you will see the seeking ones do tend to sit around near the first distraction, but that little triangle one is showing you which way it's tracing. So that would zoom off to the left, which would attract the other cats that have been distracted by the thing, as cats tend to be distracted by, and pull them away from the distraction. And then they move on to solve the problem. If you do start looking into optimization algorithms, by which I mean the kind of AI machine learning stat stuff, rather than optimizing your code, there are some known functions that are really difficult, and there's some properties that they've got, which you can read about in various places. And in fact, there's a much simpler to read article on Wikipedia that gives you a list of known pathological functions which have got, for example, the Rosenbrock function. It goes up and down, up and down, up and down, undulates. You can show mathematically that at 0.11, that's the lowest value of the function. with some algebra, so you can solve this. But lots of stats and machine learning algorithms get stuck because it undulates up and down a little bit everywhere. If you're at this conference, because you code C++, yes, most of you, there's an analogy here. Like, if you're trying to code up an algorithm, they've also, by the same score, in computer science, there are known pathological edge cases. If you're writing a sort algorithm and the data's already sorted, that's a known pathological edge case. So it might be worth stepping back if you're trying to code something up and you're trying to optimize something and it's getting slower rather than quicker. Somebody else might have already had a similar problem to you, and you might be able to find some benchmark data out there to test things on. Like, do a bit of reading and research. There's just the analogy there, because there are known things for optimization problems in machine learning space. And there are several known things in computing as well that try against different known data sets. Talk to each other. Let's learn from each other. Let's have that seeking and tracing mode and collaborate better. It's useful. Now, I set up my objective function, right, earlier on, and I passed in the max of 0 and y, which made the cats go up. Now, I could swap and send in the Rosenbrock function instead, and the cats, instead of going up, will end up down in the bottom left-hand corner, and they do end up finding it. If I start adding some distractions around that, then because I'd hard-coded the parameters, they do tend to get stuck. And I would have had a demo of them just seeking, and they don't really find it. When they're just tracing, they sometimes go off on a complete tangent because there are the undulations, so there are some bits that look quite tempting. So the seeking ones stop the cats are going for what they thought was the best leaf, because there's actually a better one over here. So sum up now, and that might give us a bit of time for me to try and make some demos work from the command prompt, because I should just stop using PowerPoint. Swarm algorithms, I've talked loads about lots of different ones, but you've got position, X, Y, X, Y, Z, X, Y, Z, W, X, Y, well, X1, X2, X3, ... Xn. That's a solution to your problem. So these are numerical solutions. You could have a mapping from a number to a category instead, but what I've shown you today is continuous in the sense I'm using doubles rather than discrete in the sense of using integers. But you could code it up as an integer and then the cats would jump to whole numbers each time. Well, that might solve a problem. So we've got this solution, but there's the idea of a trajectory in every swarm algorithm as well. So you're always driving towards the best. That's kind of what makes it a swarm, and the idea of emergent intelligence. So the whole group is greater than one individual, because the whole group's got a best position. Right? And all these things have got a for or while loop and some randomness in them. Some of the swarm algorithms have a personal best and the global best, but the cats have just got that global best. For me, and maybe for you, it might be worth you trying to code up some of these so-called AI algorithms. It really often does just involve a loop, using some random numbers, and whether that's uniform ones, or the weighted distribution, or a normal distribution. That get you some practice with some C++ random numbers. And then there's a bit of adding up and trying to decide if something's better or worse, which often just means less than or greater than. Quite simple, really. And you can actually solve some real-world problems with this, like I said, about routing, logistics, traffic through networks and things. And maybe read up some of the real-world places where people have used these optimization algorithms. But mainly go away and code these up. An extra part of the whole swarm algorithms is if you look back through the history of AI, and computers too, there's been some side points about artificial life. So we've made artificial swarms. I've talked about bees and ants and cats as well. But a guy called Reynolds came out of the idea of some boids, which is like birds, only said slightly cute, and was building on the idea of little robots moving around solving problems. And just with some rules, little rules, in each agent. They've got their own personal best, and then they can like talk to the nearby other little robots. And you can find loads of videos on YouTube and similar of little robots moving around. I'm not a hardware engineer, but I would really like to play with some robots. And you can buy some that are already built that you can just click bits into to reprogram them. But they're really expensive, so I'm just stick with being a software engineer. Like I said, I wrote a book about 5 years ago that's got these examples in. There was a mixture of some C++, Python, and JavaScript. You can draw things in the browser really quite easily. But you can also find all these algorithms on Wikipedia. Just look up optimization or swarm intelligence. Follow your nose, find one, code it up. You might be able to knock something together in a couple of hours at some point. And that might be something you want to do with your team back at work. Go, let's just do something completely different. Have a Friday afternoon coding session, but learn about something else whilst you're doing it. And it's more challenging than just FizzBuzz, but it throws up similar things about how to architect stuff and not getting distracted by the business terms about the mixture ratio and things like that. Going, no, I'm just going to have 2 tracing cats and 8 seeking cats or something. It's an interesting artificial toy problem, but if you can draw graphics in your C++, then you can see moving pictures, unless you embed them in PowerPoint and use my laptop. And if you need some practice with C++, for reasons to do with my brain not working, I've lost the QR code off that. I wrote a book that was published this year, which is aimed at people. If you've been listening to lots of the C++ talks over the last few days and gone, there's yet another new thing I don't know. C++ has got huge, and there's about 3 or 4 ways of doing anything. This book's real small, it's about 250 pages, and just zooms from C++ 11 up to, well, kind of bits of 23, just pulling on some salient bits to get you up to speed. And if you already know it all, brilliant. And if you've read it, write me a review somewhere like Amazon. And that is quite enough for PowerPoint. Let's see if I can do a demo. Anyone got any questions whilst I mess around? Stunned silence. Not surprised. And of course, I did it on different resolution. Hey. And it's not showing on that screen. It works on my machine. I guess I need to mess with the display.
That's your machine.
I'm not showing you. Yeah, I might need some help at this point again. Let's try the display settings. I suppose I could just shift the window over. It's possessed. Well, just look over there and press all the wrong keys.
Okay, let's try it then.
Yay!
I know that's all. If not, we can mirror it.
No, what might be better is if the demo goes
Oh, yeah.
on that one. So, all the cats left the bag. I'm making them go magenta as they've got high enough up. And I should have done this with a slightly different resolution. If I bring this back here, then I can see what I'm doing here. So, here they come. You can see that they're ambling around, but once in a while, one of them starts zooming upwards and takes things up. And I can switch out to, this is not ideal, sorry about this. So this one, I've switched to the Rosenrock function, so we want them to get into very nearly the bottom left corner. And once in a while, one of them will turn into a triangle, and that's doing that tracing. There's the best leaf, there's the best pigeon. And the other ones are ambling around, and you can see that we are kind of herding these cats towards the bottom left corner, just by switching the function we pass in. Might want a discussion about whether holding a standard function was the best way to do this. It was nice and simple. That might not be optimized for speed for that one. But you can see that they are gradually zoning in on that bottom left corner. And every now and again, one of them goes magenta because it's found that good enough, close enough to the answer we're actually after. And then I talked about having some distractions going on. That one's on top of, let's stop that one, and that one, and that one. Oh. But you can see the two grey circles, that's the distracted bit that does the witch's hat that's got a plateau. And they all just went, bah, not bothered by that. But I wonder which way round my parameters are. If I do it again, so different distractions, but this time I've told them not to swap modes. So the ones that were tracing kept tracing, and I took too long to get that up on the screen, but it took them a bit longer to go. Should I do it again? Maybe. Might as well. So distractions in a different place. You see how some of them are tending towards there. These are supposed to be going up and escaping the paper bag. Some of them are distracted. Some of them are not distracted. So this time I set it up so they didn't swap modes. So some of the tracing ones have managed to go, hey, I'm out of here. But now all I've left behind are the seeking cats and like I said, you've got this plateau now near the grey points. And because we're only doing the seeking, that exploiting, we've lost the exploring, tracing ones. We're not solving the problem anymore. So again, that swarm algorithm needs the both parts, otherwise you get cats going, a thing, and not like finishing the talk or escaping the paper bag. And we can run various different combinations of those. But I guess at that point, short of, I'll just show you loads more blobs moving around on the screen, practice writing some code. If some new trend like AI starts happening, you're probably clever enough to figure out some of the essence of it. People will hide behind buzzwords, and that might be quite confusing or overwhelming. Get to the nub of it, because we are, well, whether we're engineers or crafters or whatever, because we know some technical stuff, we can get to the heart of some of this and go, and it often is just a for loop. And almost all AI is just doing something a bit random sometimes. But that does let you solve some problems. And you do that when you're trying to solve a problem. If you sketch something out with pencil and paper on a whiteboard, you try something and go, rough that bit out, move that bit. You start somewhere. So if there's a topic you don't know, and for me that was drawing pictures in C++, try it anyway. It might go wrong. You might give yourself a score of 1 out of 10. But next time you try it, you might be able to improve. And you might need that kind of swarm intelligence thing, where we talk to each other and go, actually, no, I found it was better over here. Let's collaborate, talk to each other, and we might see some emergent intelligence. And that's all I've got to say, really. Thanks for listening.